Everybody knows about climate change now because the consequences are severe. In the Antarctic, there are it's almost 30 degrees now at the moment, so that's 13 degrees, which is really high for this time of the year. So this is in the headlines now, so it's good that there's research done in this field. What are the consequences? What are the issues of climate change? So the Wegener Center in Graz is often also quoted in the media because they research in this field. So thank you, Mr. Truhetz, for being with us today talking about these issues. Thank you very much, ladies and gentlemen. Thank you for inviting me to this symposium. I'm glad to be able to be here and talk about climate change on a global scale and in Austria. Just a moment, how can I switch to the next slide?
Okay. Jetzt kommt's. Ja, wunderbar. Super.
Okay, perfect. It works now.
Okay. Gut, ja. Ich möchte mich allerdings auch noch
Well, I would like to thank somebody else too. Especially the project Reclip Convex, which is a research project together with the Austrian Society for Meteorology and Geodynamics. So here we have research for climate protection and, of course, the Cordex FPS project, which is an international initiative which tries to produce high-resolution climate simulations. So what would I like to talk about today? I could divide it into 3 points. First of all, I would like to show you the history a bit, what has happened so far, what do we already know about climate change according to scientific data, and then I would like to talk about what the future holds for us. Here I will base my statements on scientific research again, and finally I would like to conclude with some conclusions about hail. I'm sure you know this curve already. Last year, the latest report by the IPCC was issued, and they found that the global temperature development has been continuing since the 70s. You can see this over land and also over the oceans. We can see continuous increase in temperatures. So at the moment, so this is the period for comparison from 2011 to 2020 compared to 1850 to 1900. So you can see in the first 50 years and now we have 1.09 degrees Celsius higher temperatures. In the last report, there was talk about 1 degree. So here we can already see a progressive increase in temperatures. Maybe you remember in 2012, 2010, 2012, we discussed the so-called hiatus. We thought that the temperatures wouldn't rise anymore. We weren't sure if climate change really exists. Well, the following years have shown that there was no hiatus. There was a continuous increase in temperatures. Well, what else can we say? In the last report, 2013, they found that the Arctic ice extent had a speed of percentage of 3.5 to 4.1%. So that's the reduction per decade, and now we're at 12.7% reduction per decade. So climate change is really accelerating compared to the last IPCC report. And also the ice shields are melting, so not only the sea ice, but also the ice on land is affected, especially the glacier on Greenland is affected, is melting. And you can see in the diagram the loss of ice mass since 1990, which also contributes to higher sea levels, which we can see here. So we can also see a progression here. In 2013, they found 1.7 to 2.3 millimeters per year, and now we are sure that it's 2.3 millimeters per year or even more. So we can see that the whole planet is now being affected by climate change, the whole climate system. Here we can only see an example. You can see the land masses of the Earth: North America, South America, Africa, Europe, Asia, and Australia in a symbolic depiction. And we depicted here are the areas where we believe we can already see significant change in heat extremes. And you can see that this is practically the whole planet. You can find these diagrams also in the current IPCC report. There are maps also for precipitations and other extreme weather conditions, and they will all show pretty much the same picture. How about the alpine area? This has already been talked about before by Mr. Lazar. Here we have data which have been collected in the whole alpine area, which are already a bit dated, but this doesn't really change anything about their current significance. So the red line here shows the average increase in temperatures per year. And you can see that especially lately we have really strong rising temperature trends. Usually we say that temperatures in the alpine area rise about twice as quickly as globally. And we can also say that that air pressure has increased, and the number of sunshine hours too. Because of climate change, we see a change in the weather conditions, in their occurrence. So weather conditions are changed in when they occur. So it changes when they occur, and this has also been talked about already before. So we also have higher air pressure. We have more good weather conditions. And the question, of course, is how will this continue? What else can we see? This also is a result from the Association for Meteorology and Geodynamics. So if it rains, how does the intensity of precipitation change? This you can see on the left picture. In summer, you can see a significant increase, an average increase in Austria in general, especially here in eastern Austria. It is more than 10% increase in intensity of precipitation. So in winter, there are some increases, but also some reductions. What else can we say? In Europe, there is data on precipitation and temperatures, and as temperatures rise, there is also more vaporization. So the whole process is accelerated. So we can see here the type of precipitation event. So this is not an event with hail, but this is a stratiform precipitation extreme, which are increasing with about 7% by 7% per 1 degree temperature, a rise in temperature. So we can also see that the convective precipitations increase by 14% per degree Celsius. This is called the Super-Clausius-Clapeyron effect. We can also see something completely different. The greenhouse gases increase in an unstopped way. So we have here the historic development where you can see that the curve just really goes up. Here where here we see carbon dioxide depicted, and we can see how much it has already derived from the natural development. How much it has already deviated, sorry. So at the moment we are at 460 ppm. So this, of course, has an effect and has consequences. So per year, we emit about 9.4 gigatons from combustion of fossil energies into the atmosphere, plus 1.6 gigatons carbon dioxide because of our use of forests and land. On the other side, oceans take up about 2.5 gigatons of carbon dioxide. And on land, 3.4 gigatons are being absorbed by the ground. And this means that we have 5.1 gigatons of carbon dioxide, which goes directly into the atmosphere. And this means that there's a rise of 2.4 ppm in carbon dioxide emissions per year. half of the carbon dioxide that is absorbed on land is absorbed by rainforest, and this is another problem we have because of the strong use of rainforests, because so many trees are cut down. The rainforest is developing from a place that can absorb carbon dioxide to a place that produces carbon dioxide. So you can see it here in the diagrams. You can see the net balance of carbon dioxide emissions, and you can see that the rainforest could become a producer, an emittent of carbon dioxide instead of absorbing it. So how could this continue? This is in our hands. Climate protection is talked about a lot at the moment. There's also climate change, adaptation to climate change, but climate protection is the primary goal in order to reduce the effects that we will then have to adapt to. More results for Europe. Here we did a special research for Europe, for the climate in Europe, for climate signals of climate change. We can see here an increase in temperatures in a worst-case scenario. So this would be more than 5 degrees Celsius in this worst-case scenario, RCP 8.5. You can see that the alpine area is also particular in the context of climate change. And when it comes to precipitation, we can see in Northern Europe, including Austria, the alpine area, there is an increase in precipitation until the end of the 21st century. So this means, what does this mean for Austria? The number of hot days would increase on average. It would be 7.4 days on average, which is a lot more than we have today, and also longer heat wave periods. So if we have weather conditions like we have in winter, in summer, then we have heat waves, and they will become longer and longer. What will be going on with precipitation? We can see a strong increase of precipitation in winter. Funnily enough, this year it is very dry, but this is also just the moods of nature. So there can be various events every year. However, in summer we can see that there is contradictory models. We cannot really say how much precipitation we will have in summer. What conclusions can we draw from all of this when it comes to hail? These are more qualitative than quantitative statements. The models we have seen are climate models which show us a resolution of 12 kilometers approximately. And we've seen on the radar images how small the thunderstorms actually are. So to depict them adequately, we need models with much higher resolution. So there have been experiments to do that. You can see here a climate model with not such a high resolution, where we see thunderstorm cell which fits into one cube, so we cannot actually make a lot of draw a lot of conclusions from this. This is why we can never be quite sure that our models give us the right information. What we can do here now is to dissolve this process physically. So here we speak of convection permitting models, which really give us added value. Here is depicted the average precipitation over one day. So you can see the hours of the day, and you can see the black line. This has been done in Switzerland. The black line is the measured precipitation over the course of one day. So in the late afternoon, we have the thunderstorms. So if we do simulations like this with common climate models, then we don't actually see the thunderstorms in the afternoon. We don't see the peak in the afternoon, so it is not depicted correctly. Only if we use convection permitting simulations with higher resolution of 2 kilometers, that's the red line, then we can actually depict the natural phenomenon of the thunderstorm. And we can see this phenomenon also in the eastern Alpine area. We can see it in England, in Germany, in Baden-Württemberg, and also in Belgium. We can see how the higher resolution really adds to the correctness of the model. So there have been first simulations with this high resolution. I would like to show you some examples. The change in precipitation intensity in 3 kilometers dissolution compared with 12 kilometers resolution. So we have 12 simulations, and this means that we can already draw some conclusions from there. Precipitation intensity is much higher in the Alpine area in the 3 kilometers resolution compared to the lower resolution of 12 kilometers. So when it comes to thunderstorms, we can actually not say much if we use the old models. We need convection permitting simulations, and they show us an increase, a significant increase, which we wouldn't have expected otherwise. Another example from England. Here, there was no change in precipitation in the old model, and then if you use the new resolution, then you can see significant precipitation. So, to make it brief, I would like to show you another diagram for hail phenomena. So I'm not actually a hail expert, but I understood that we need an unstable layering of air masses up to 50 meters per second of upwind, updraft, and the smaller, so the parts are propulsed upwards and freeze and then fall down, and as they fall down, they grow and encounter supercooled water droplets and keep growing, and this is how they reach the melting point, which means that parts of the hail stones will start to melt, and what then reaches the ground is what we then actually see, and we go in with the planes to try and reduce the size of the hailstones. So what do we have to expect with climate change? Generally, there's more hydrogen in the atmosphere. This means that we have stronger updrafts. So the vertical extension of the atmosphere is also increasing because of the higher temperature. So the melting point, the melting height, is higher. This means that the hailstones which fall from melting height have a longer way towards the ground. They are longer. They are in the air longer, so there is a higher probability that they will melt. So scientific researchers actually agree that there will be fewer small hailstones, and there will be more larger hailstones. So the potential damage is much higher. Okay, I would like to sum up briefly. So climate change proceeds unstopped, but it is in our hands to change it. In Austria, we are confronted with more increases in temperatures. We need to expect more precipitations in the winter. We can also see in recent simulations with convection permitting scales that they really deviate from the standard models we had so far. So we have a huge demand of research here, especially also when it comes to hail formation. Of course, all this is not actually depicted or only depicted marginally in climate predictions. But we can predict that there will be more hail in the alpine area and that there will also be larger hailstones. So this is the main points summed up. Thank you very much for your attention. And I have reached the end of my presentation. Thank you very much. You are not quite at the end yet, because there's also the possibility to send in questions. michael.kerner@gmx.at or just comment next to the video. As a researcher, you are of course challenged in these kinds of times. So you have a worst case scenario. Should we have done more already in order to escape this worst case scenario? Do you feel like you're not being heard as a researcher? Well, as a researcher, you actually never feel heard. Actually, the worst case scenario, which I have shown now, that's actually experts agree that this is not very probable. The reason for this is that the greenhouse gas concentration scenarios are based on the development of demographics. So we base it on how we think demographics will develop. There's various factors to consider: regional conflicts, technological development, and so on. So all these are bases on which we do these simulations, which mean that prices for fossil energies will rise in a way that economy can't actually deal with it, so we cannot afford it. So this might have a self-regulating effect in a way. And today we actually see just how dependent we are on fossil energy, especially due to the geopolitical state at the moment. And we can also see how volatile things are. So the main insecurity is actually how humans behave. And it's very difficult to predict human behavior. So if there's no more questions from the audience, then thank you for your presentation and all the best. And it's very good to be in touch with you and have an exchange on climate change. Thank you.